Okay, so these are the PowerPoints. This is the lesson for equilibrium constants. Okay, now first of all, the equilibrium constant is Kc. Everything's a constant. And if you remember with KSP, that was done simply for the, wait for it, it's back, the lightsaber. KSP was done simply just for the products. Okay, the Kc, which is always when you do equilibrium, is products over reactants. Okay, so in this equation, what we have is we have H2 and I2 react to form 2HI. So products go on the top. So there we go. And look, we've got the 2 here coefficient, just like in KSP, that becomes squared. And we have the molarity of H2 times the molarity of I2. So that's how you write an equilibrium expression. Obviously, if there were a 3 in front of here, this would make this coefficient, or the coefficient would turn into a 3 for the exponent. That's the equilibrium expression. Okay, so here's our problem. I'm going to go ahead and redo the problem. Here's the setup down here. And I'm going to go ahead and redo this on the next slide. Let's go. We've got 1 mole of hydrogen, 1 mole of iodine in a 5-liter reaction vessel. So moles divided by liters, we can find the molarity of each. Temperature matters, but it's not involved in our calculations. Forms hydrogen iodide. The concentration at equilibrium is 0.0440, and that's just of I2. Okay, moles per liter. Calculate the Kc for the reaction. All right, so here's our equation. H2 plus I2 forms 2HI. Okay, now first of all, if we know the concentration at equilibrium of I2, then we also know the concentration of H2 because they have to be the same. Okay, so what we're going to do is, as mentioned earlier, we have 1 mole of hydrogen, 1 mole of iodine, divided by 5 liters. That's going to give us our starting molarity. So it's going to give us 2 molar solution. So let's start with that. 0.2 molar of hydrogen, 0.2 molar of iodine. Okay, we don't start with any HI, so we've got a 0 there. So whenever you do equilibrium, we want to do a start, change, and final table. Okay, so we just filled out our starting concentrations. Okay. Now, the next one, we have a final value. We are given that in the problem. Final value of iodine is 0.0440. So we're going to put that in here. If we know the final value of iodine, well, then hydrogen has to be exactly the same. They combine. Anytime you use one iodine, you also have to use one hydrogen. Okay. All right. So what we can do now is calculate the change. A little lightsaber out. If we start with 0.2 molar and end with 0.044, that means we must have lost 0.156. Okay, so 0.2 minus 0.044 equals 1.56. I'm going to put a negative there, just meaning we're losing that or using some of it up to produce the hydrogen. Well, 0.2 subtract 0.044 again, we're using the exact same amount of iodine. Okay, where did all that go? Well, let's get this straight. Anytime we use one hydrogen and one iodine, we are always going to produce 2 HIs. So if we know the concentration of one of these, let's say iodine, we know HI is always going to be twice that amount, just like with the KSPs. Okay, so think of that conceptually. So if we lost or used up 0.156 of the I and the H2, then that means we must have produced twice as much HI, because for every one I, we produce twice as much HI. Okay, so 0.312 is twice that of 0.156. Notice I put a positive there because we made some of it. Okay, well, obviously 0 plus 0.312 is going to be our final value. Okay, so now that we have the final values, and the final value means at equilibrium. Okay, so anytime you see the final, that's at equilibrium. So once it finally stops. Alright, so what we're going to do is we're going to take all these values and plug it into our equilibrium expression. So our expression is products over reactants, so HI squared, right, over H2 concentration and I2 concentration. Okay, so what we're going to do now is take 0.044 and plug it in for hydrogen. 0.044, plug it in for iodine. 0.132, plug it in for HI, and then we're going to square that one because we're plugging it into the equilibrium expression. Okay, so that's what I did down here. Get my lightsaber out. Alright, so HI is going to be on top. So the concentration of HI is 0.312, so I plugged it in there, and then I'm going to square it, and then the products of, oops, there it is, 0.044 and 0, so this is H2 right here, and this is I2. Okay, so you got to square that first, then go ahead and divide it by the products of those two. That gives you 50.3. And that's how you find the Kc, which is the equilibrium constant. Okay, so the next slide I'm going to do the exact same problem. I'm just going to fill it out so you can see it one step at a time. Okay, so this is the exact same problem. I'm just going to work it out one step at a time. Okay, so it gives us 1 mole of hydrogen to start with and 1 mole of iodine. So if we do 1 mole divided by 5-liter vessel, that's where we get our concentration. Okay, so very important, make sure you put concentration in here. So it says we start with a 0.25 molar solution of each of those. And we don't start with any HI. Okay, and then the last piece of information it gives us is the final value of iodine, which is 0.0440. Okay, all right. If we know iodine, its final concentration, we know hydrogens. They have to be the same. Okay, those two combine. Anytime one I is used, you also have to use an H. Okay, so we know the concentration of H at equilibrium, which is our final, must be the same. Okay, so now we can go ahead and do the change. So basically 0.2 minus 0.0440 gives us, whoops, boy, getting a little crazy with the lightsaber here. Put a negative sign just so we know that we lost some of that. Okay, and let's think about this conceptually. When we lose some of that, where does it go? Well, it goes to make the HI. Okay, so that must have increased. Okay, so how much does it increase? Well, let's think about this. We've got, alright, forget the sound for a minute. For every one H and one I, we produce twice the amount of HI. Okay, so for every one H and one I, we're going to produce twice that amount. So it's basically going to be twice the 0.156. Okay, so that's going to give us 0.312. Alright, and then we're going to go ahead and add those together. And then from here we can go ahead and plug in, these are our final values. That means once they're at equilibrium, we're going to go ahead and plug it into our equilibrium expression, which is HI over, and that's squared because there's 2 HI, over H2 times I2. Okay, so we can plug these values in here, 0.312, and then we got to square that, and 0.0440 times 0.0440, or just that squared is fine, and that gives us a constant of 50.3. Okay, so this problem is basically just the opposite of the last one. In this particular problem, they're going to give us the Kc, the equilibrium constant, and we need to find the final values of each of the concentrations. So it's just the opposite. So it says concentration of H2 is 0.01, of I2 is the same thing, 0.01, and HI 0.02. Okay, so those are the concentrations we start with. So I went ahead and plugged those values into the table down here. It says, what are the concentrations at equilibrium? So in other words, what are our final concentrations? That's at equilibrium. So we're going to set ourselves up with the exact same equation. And here's what we do a little bit different in this problem. Okay, we don't know the change. Now what we got to figure out, we have to determine which way is the equilibrium going to shift. Okay, is it going to shift to the right, meaning making more of the HI, or is it going to shift to the left? We don't know which way it's going to. So here's what we're going to do. We're going to basically take our start, change, and final values. We're going to plug them into our equilibrium expression, and we're going to see what we come up with, what value we come up with. Okay. So 0.02, and we're going to square that. So that's, I just plugged 0.02 in for that. 0.01 times 0.01. Okay, so again, the reason we're doing that is to figure out whether it shifts to the right, making more HI, or shifts to the left, making more of each of those. Okay, so we're plugging this in. If we square the top, that's going to give us 0.0004 on top, and on the bottom 0.01 times 0.01 gives us 0.0001, and then divide those, you simply get 4. Okay, so let me ask you this. If at equilibrium, what value should that be? Well, let's look at our equilibrium constant. If it's at equilibrium already, it should be 50.3. It's not. Okay, this value is too small right here. So this 4 is too small. We have to make it larger. How do we do that? Well, we do that by, just think about this mathematically. How would we make 4 a larger number? Well, two things. We could increase the top value, which is HI, right? So increase the concentration, or we could decrease the bottom value, okay, which are basically the same thing. So what that means is, remember the top is HI. We're going to increase HI. So what that means is our shift is going to shift to the right. Okay, so what that means, one more time, is we're going to shift to the right. In other words, we need to make 4 larger. Okay, it's going to happen. 4 is going to become larger until it gets to 50.3, which at that point means it's at equilibrium. Okay, how do we make 4 larger again? We increase the concentration on the top. What's the top? It's HI. So that means we're going to shift to the right, meaning we're going to make more of HI, and at the same time, so this is going to increase. At the same time, what are we going to use to do that? I2 and H2. So those are going to decrease. Okay. So if it were larger, let's say, for example, it was 100. Okay. This value ended up being 100. Well, what would happen is we would need to decrease it until we get to the equilibrium constant, 50.3. Okay. So we'd do just the opposite. It said it would shift the entire thing to the left. Okay, so we said it's going to shift to the right. That means the right is going to increase, so HI is going to increase, and both of these are going to decrease, meaning we're going to lose some of those. So we're going to make H2 our X, I2 our X. We don't know how much they changed, but we know they changed by the same amount, whatever they are, and we know they decrease because we found that out. Okay, and then we know that HI is going to increase. Okay, and we know whatever I decreases, HI is going to increase by twice that amount. Okay, so just remember, look at your coefficients there. Think of it conceptually, it's the same as the KSP. Alright, so what is our final? Well, it's start, minus change, so that goes down there. I is start minus change, and then HI is start plus change, which is 2x, so it gives us that. Alright, so now what we're going to do, we have the final values, and those are the values at equilibrium. We're going to plug it into our equilibrium expression and set it equal to 50.3 and solve for x. That'll be the next slide. Okay, so let's plug it into our equilibrium expression, which is HI squared divided by H2I2. Okay, remember we determined that the equilibrium, that the final for HI was 0.02 plus 2x. Well, we need to go ahead and square that. Okay, so let me just show you. The bottom one is 0.01 minus x, that's H2, and 0.01 minus x, which is I2. Well, those two things would just be that number squared. So you can write it like this, or you can put them squared. I like them squared because you can then take the square root of both sides, which is what we do in the next one. Okay, so the next one, if we take the square root of both sides, it gets rid of the square on the bottom, it gets rid of the square on the top. What we do to one side, if we take the square root of one side, we got to take the square root of the other. So we also have to take the square root of 50.3, which gives us 7.1. So now we're at 0.02 plus 2x divided by 0.01 minus x equals 7.1. So all I did was took the square root of both sides here. Okay, and it gave me this equals this. Okay, so now we need to go ahead and simplify. So I'm going to multiply both sides by by 0.01 minus x. Okay, so if I do that, 0.01 minus x, those will cancel out. 0.01 minus x. Okay, and that's what we're left with down here. Okay, so that's what we're left with. Alright, from there we need to go ahead and distribute the 7.1. Okay, and that's the next step. That's what we get. And then we'll go ahead and add both sides. Okay, so 0.71x, which gives us 9.1x. Then what we need to do is we need to subtract 0.2 from both sides. Okay, and it gives us 9.1 x equals 0.05. Now we just divide both sides by 9.1. Oops, I'm sorry. We're not dividing both sides by 9.1, we're dividing both sides by x. Okay, and that finally gives us x equals 5.6 times 10 to the negative third. Okay, now we need to go back to our original equation, our final expressions, our equilibrium. Plug in x into 0.01 minus x. Remember that was H2 and I2. And that gives us 0.004 for both H2 and I2 because they're the same. Then we'll go ahead and plug x in for 0.02 plus 2x. That's HI at equilibrium, and it gives us that.